Welcome back to this next video in which we are discussing topological spaces. Okay, so we've now seen the abstract, rigorous definition of a topological space, and we've seen that a topological space can be built from any arbitrary old set that you have. Okay, so you just take this arbitrary set, capital X, and all you have to do to turn it into a topological space is build this structure called tau, which is called the topology, which is a subset of the power set of X, which obeys these three fancy properties down here. Now, the first thing that I should stress is that there is not just one topology that you can construct for any set capital X. Okay, there are loads of plausible topologies. Okay, and in fact we're going to show two different topologies that you can always build for any set that you've got capital X in a moment, called the chaotic and discrete topologies. Okay, they're a bit useless, but they are extreme, easy to construct examples. Okay, so it's certainly not true that for some set there's only one topology that you can build. There are loads of different topologies that you can build. Okay, all you have to do then is get a subset of the power set of X that obeys these axioms, and then it is called a topology, and then the set with that topology alongside it is called a topological space. Okay, right, so what we want to do at the start of this video then is explore the definitions of what is meant by an open and closed set, and these are just nomenclature, so that's the easy bit. And then what we'll go on to look at is examples of building topological spaces, and we'll hope to get some intuition as to why doing this actually captures this concept of what is near to what inside this set that we aimed to actually capture with this structure. Okay, now I am not in this video going to be able to actually justify why we insist on having these three axioms. That will come from the rigorous abstract study of topology, specifically looking at the definition of continuous functions between two topological spaces. But what I do aim to give you the intuition for in this video is why we look to a subset of the power set of a set in order to actually capture this notion of what is next to what in the set. Okay, so that's the intuition that I hope to have given you by the end of this video, and it's not particularly rigorous, but it does help to understand really why we looked to a subset of the power set of X, to a set of subsets of the set capital X to capture this concept. Okay, right, but before that, let's just do some nomenclature. Okay, so an open set then. An open set in a topological space is exactly a subset of the set capital X, which is in the topology. Okay, so how am I going to write this? If U is a subset of the set capital X, and U is an element of our topology tau, then we call U open. Okay, so I'll just add that on. Then U is open. Okay, it's just a piece of nomenclature, so all the subsets of the topological space that are actually in the topology are called open sets in that topology. Okay, so the notion of an open set requires the notion of a topology in order to define it. Okay, if you've just got a set, if you're just working with set theory, there is no, you're talking nonsense if you talk about a set being open or not. An open set requires more structure to be defined on the larger set capital X in order to define that concept. Okay, you need a topology before you can call a subset of that set open or not. Okay, right. The next concept then is a closed set. Okay, now the concept of a closed set is not, and this is important, it is not just not open. Okay, that's what people generally misinterpret closed set to mean. Okay, people interpret a closed set as a set that is not open, any subset that is not in the topology, but that's not what the definition of a closed set is. Okay, a closed set, okay, so if, let's say, what should I call this set? If A is a subset of capital X, and the complement of A in X, so I'll write it like this, X take away all the elements of A, so the complement of A in the set capital X is an element of the topology. So if the complement of the set capital A is an open set, then we call A a closed set. Okay, so then A is closed. Right, so just to draw a simple picture to capture this concept then, if we've got our set capital X here, okay, and we've got some subset which is capital A, then the complement of the subset capital A in the set capital X is all of this portion, all of the bit that isn't A in the set capital X. So this is the complement of A in X, this portion here. And if that is an open set, if that's a subset that's in your topology, capital Tau, then we call A a closed set. Okay, so it is absolutely not the case that all closed sets are not open. Indeed, some sets are both open and closed, even though obviously it sounds like quantum mechanics, but the nomenclature is bad. Okay, open does not mean that it can't be closed. Sets can be open and closed. So to give some examples of sets that can be open and closed, consider these two subsets, the empty set and the entire set capital X. These are always in the topology. That's axiom number 1 of a topological space, that they're always in that subset of the power set Tau. Okay, so they're absolutely always therefore open sets. But I claim that both of these sets are also closed sets, and the reason is that if we consider what the complement of each of these subsets is in the set capital X, in the topological space capital X, I claim that those complements are also open sets. So let's start off with the empty set here. So we're now putting in place of A here the empty set. It's certainly a subset of capital X, and the complement of the empty set in the topological space X is going to be X remove all the elements in the empty set. Well, of course, there's no elements in the empty set, so you haven't removed anything. So that's the entire space, capital X. And of course, that is an element of the topology. It is an open set. So indeed, the empty set therefore satisfies the definition of a closed set. And in addition, if you do the same thing with the entire set capital X, okay, so if you let A now equal the entire set capital X, again that's a subset of capital X, and if you take the complement of X in X, then you remove absolutely all elements of capital X, and you're left with the empty set, and the empty set is an open set, it's an element of your topology, and therefore the entire set satisfies the definition of a closed set as well. So these two sets here are examples, convenient examples, of sets that are both open and closed, and some people will use the terminology clopen for these sets, so they'll call them a clopen set, sets that are both closed and open. Okay, so those are counterexamples to the notion, the misnotion that an open set cannot be closed. Okay, right, so that's all the nomenclature that I want to introduce in this video. Let's now go on to some examples of topological spaces. So it's always good to start off with a really simple example. So we're going to firstly apply the definition of a topological space to a finite set, because that's something that we can actually write out on the piece of paper, and therefore we can get some intuition for this. Okay, so let's start off then with our set capital X as a finite set, and we'll take this finite set that just consists of 3 elements, so the elements 1, 2 and 3. Okay, so this is going to be our finite set here, and then what I now want to do is take this set and turn it into a topological space. So I want to define a topology on this. Okay, and we're going to use this to get some intuition about topological spaces and to try and piece together an understanding of why this notion captures the concept of being near to. Okay, right. So let's build a topological space then. Okay, so what we need to do then is build a topology Tau. Now we know that our topology must always contain 2 subsets of this set capital X. It always has to contain the empty set, and it always has to contain the entire space. Okay, so we might as well put those in right away, because we can't not put them in. Okay, so I'll start by putting those in right away here. Now my first question is, do I need to add anything else? Could I just leave it at that? Is this a topology? Okay, so let's question that. Is the subset of the power set which just contains the empty set and the entire space, capital X, the entire set, capital X, is that a topology for this set, capital X here? Okay, well let's see if it obeys the axiom. So it certainly obeys axiom number 1, it contains the empty set and the entire space. Let's see if it obeys axiom number 2 and axiom number 3. So axiom number 2 says that if we intersect any two subsets from our topology, that we must get another element of our topology. So there's only 4 possible combinations of what we can intersect. We can intersect the empty set with itself, but when you do that, you just get the empty set, because there's no elements in the empty set, so when you intersect it with anything, you get the empty set back again. So the empty set intersect with itself is just going to give the empty set. For the same reason, the empty set intersect with X, either way round, is just going to give the empty set. Okay, and then the only final thing that we have to consider is X intersect with itself, and of course that will just equal X. So it seems to obey axiom number 2, that if you intersect any two subsets from the topology, you will get another subset that's in the topology. Okay, so axiom number 2 is done. Axiom number 3 then, that if you union together an arbitrary number of subsets that are in your topology together, you will end up, or you must rather, end up with another subset that's in the topology. Okay, so if we union together then an arbitrary number of subsets, well, there's only 2 subsets in here, so we can only, at the very best, union together 2 subsets. Okay, and if we do union these 2 together, the empty set unioned with the set capital X, then of course we will end up just with capital X again. Okay, alternatively we could end up, of course, unioning together the empty set with the empty set, or X with X, but those will give answers back in here as well. The empty set union with the empty set is obviously just the empty set. X union with itself is just going to give X. So indeed, all of the answers to unions as well lie back within this set. Now you'll notice that those arguments that I just gave, they didn't have anything to do with this actual set that I was using, capital X here. So in fact, it's not just the case that this is a topology for this specific set, it's actually a topology for any set capital X. Okay, so this is always a trivial example of a topology, and this topology is what's known as the chaotic topology. Okay, and you can absolutely always put the chaotic topology on any set capital X that you've got to turn it into a topological space. Okay, right, so you can imbue a set capital X with the chaotic topology to make a topological space. Now, what I would also like to tell you about is another example then of a topology that you can always create for any subset capital X, okay, not necessarily for this one. So another topology that you could take is then the power set of X. Whoops, and I've changed my notation now, which doesn't help. I'll try and be consistent with my notation, so I'll have the big curly P here. Okay, so the power set of X, and in this case I think to give you a bit more intuition I will write out explicitly what the power set of X actually is. Okay, so it's the set containing all subsets of this. So we'll have the empty set and the entire set in there instantly, but then we'll have all the subsets that just contain a single element. So we'll have the subset containing just 1, the subset containing just 2, the subset containing just 3, and then we'll have all subsets that contain 2 elements, so we'll have all possible combinations of 2 elements. So we'll have the subset containing 1, 2, the subset containing 1 and 3, and finally the subset that contains 2 and 3, like so. Okay, so there is the power set of X in this case. So if you were struggling with the concept of the power set of X, I hope that has made it explicitly obvious what that actually means. Okay, now, not only for this set capital X, but for any set capital X, I claim this is always a topology that you can use. Now let's just understand why that's going to be the case. So let's make sure that it obeys the axioms of a topological space. So axiom number 1, we need to make sure that the empty set and the entire set are elements of this topology tau. Well, of course they are, they're certainly there, they are subsets after all, so they're always going to be in the power set of X. Okay, now we need to make sure that if we intersect any two subsets from the topology together, that we end up with another element of the topology. Well, whenever we intersect two subsets of a set together, you will always end up with another subset of X. That's pretty much a trivial statement. The worst case scenario is that the two subsets that you're intersecting have zero intersection, and then you'll end up with the empty set. Okay, but you will always end up with a subset of capital X back again. So whenever you intersect two elements of the power set of X together, you will end up with another element of the power set of X, because the power set of X contains all subsets. So because whenever you intersect two subsets together, you end up with another subset. Okay, I mean, what else would you end up with? It will be back within the power set of X, because the power set of X contains all subsets of the set capital X. And the same is true of unioning together subsets. Whenever you union together two subsets, you do end up with another subset. The worst case scenario, or the most extreme case, is that you just end up with the entire set capital X, but that's still a subset. Okay, so again, you will end up with something that's in the power set of X, because the answer will always be a subset. Okay, and those arguments, again, never did I use the fact that we were working in this really simple set, so it applies for any set capital X that you like. Okay, so you can always put this on as a topology to any set, and this is called the discrete topology. Okay, so what I would like to do now is try to give you an insight into why taking a subset of the power set of X, or defining this topology, defining this set of subsets of the set capital X, is a way of actually capturing this concept of next to. What elements are next to other elements? And it will be nice to do this with the finite set, and then we'll go on to the infinite set. We'll go back to the plane. Okay, now, I want to say that what I'm about to do, it's not going to be fully rigorous, but it is going to give you good intuition for why we have a subset of the set capital X that captures this concept of what is next to what. Okay, as I said previously, I'm not going to be able to justify to you why we insist on it must having to obey those three axioms. Those will come when we look at more advanced concepts in topology, such as continuous functions. But I hope at the moment to justify, at least to some extent, why we look to subsets of the power set of X to capture this concept. Okay, so enough talking, let's actually see what I've got to say. Okay, so how then can I get a notion of what is connected to what in this set using these subsets of the power set of X, using these sets containing subsets of the set X? Okay, well, this is the idea. If you want to know what is going to be connected to the element 1, okay, so we've got this element 1, and remember, the intuitive thing that we are trying to do is draw lines in between these elements in this set to try and understand what is connected to what is next to what. So we'd like to draw lines in between these. How can we use these topologies, these sets of subsets of the set capital X to draw lines? Okay, well, I'm going to draw a line between two elements in this set if, for any subset in the topology here that contains one of them, the other one is always present as well. So I'm going to draw a line between 1 and 2 if, in all of these subsets that contain 1 in this topology here, I have 2 also there, and vice versa. So in all the subsets that contain 2, I also have 1. So if these are always found together in any of these open sets that are in the topology, then I'm going to draw a little line in between them. Okay, so to do an example here, let's do it for the chaotic topology here, and you'll start potentially to see why this is called the chaotic topology. Okay, so if I want to draw lines to connect the elements of this set then, okay, well, of course, we have the empty set. That doesn't tell us anything because nothing's in there, and then we just have the entire set. So that means that I can draw a line between every single one of these. So what I'll end up with is something that looks like this, basically. Why? Because if I want to ask, should I draw a line between 1 and 2, I ask, are these two elements always together in all of the open sets in the topology? Well, neither of them are in the empty set, so that doesn't matter. Okay, that doesn't screw us at all, that doesn't break this, okay, because neither of them are in there, so it doesn't violate them not being together. Okay, I'm not insisting, and this is important, I'm not insisting that these two elements have to be in every single subset. I'm saying that when one of them is in a subset, the other always has to be there as well. Okay, so I then move on to my only other open set here, which is the entire set capital X, and of course that contains everything. So 1 and 2 will be together in that, so I can now draw a line between 1 and 2, because whenever one appears in a subset in the topology, the other is there, because the only subset that I'm having to look at seriously is the entire set. But don't just stop there. I can go now to ask, should I draw a line between 2 and 3? And again, they appear together always when they do appear. Okay, so the only place they appear is in the whole set here, and they appear together, so 2 is together with 3, so I'll draw a line between those two. And then for 1 and 3, to decide whether I should draw a line between 1 and 3, again, in the only subset in my topology where they actually appear together, they do appear together. Well, where they appear at all, they do appear together. Okay, so I can draw this little structure here. I can draw lines between all of the elements of my set. Okay, and this is really what the chaotic topology does for any set that you put it on. It draws lines between every single element in that set. Okay, because if we were to put this on an arbitrary set, capital X, then all of the elements of that set would be connected to all others, because the only place that they'd appear is in the entire set. Okay, that's the only subset in which any element of the set capital X would appear, and then it's appearing with every other element of that set, so we can then say that we can draw a line between the two. So the chaotic topology then is where all the elements of the set are connected to each other. You have a line going from any element in the set to every other element, and that's true for every element, so you just have to connect every element of the set, and that's why it's called the chaotic topology, because it's chaos. Okay, all of the elements of the set are connected to every other element of the set if you've got the chaotic topology. Okay, they're next to every other element of the set. Okay, now it's the exact opposite case for the discrete topology. Okay, so if we now look at the discrete topology on the same set here, so we'll use the set 1, 2, 3 now, and we're going to ask, should we draw lines, should we connect, should we put elements of this set next to other elements of this set? Okay, well, the way I'm going to decide this is, let's start with asking, should I draw a line between 1 and 2? Well, what I need to do is ask, is it the case that in all of these subsets, if one of these elements appears, the other appears with it? And the answer is clearly no here, because look, here is the set that contains 1 on its own, okay, and it's not appearing with 2. So 1's appearing in this subset here, but it's not with 2, and therefore it's not the case that in all the sets where 1 appears, it's also together with 2, and therefore we're not going to draw a line between 1 and 2. Now let's ask the question, should we draw a line between 2 and 3? Well, again, the same problem. We've got this set that contains 2 on its own, okay, and to draw a line between 2 and 3, I wanted it to be the case that in all the sets where 2 appeared, it was together with 3, and vice versa. In all the sets that 3 appeared, I wanted it to be together with 2. Okay, so I wanted these always to appear together if they appeared at all, and that's not the case obviously in here, because I've got the set that contains just 2. So I'm not going to draw a line between 2 and 3. And then the same is true for 1 and 3, because 1 is on its own there, so it's not appearing with 3 whenever it appears, so those two aren't going to have a line drawn between them either. So I'm not actually going to draw any lines at all, hence they're all going to be on their own. They've got no neighbours, they're next to nothing basically, okay, and that's why it's called the discrete topology. Everything's apart. And again, this argument extends for an arbitrary set capital X. If you have the discrete topology, then you're going to have all of the subsets that just contain each and every element on their own, and therefore I'm not going to actually be able to draw lines between any of the elements in that set. So indeed, all of the elements are just going to be with nothing next to them. They're all going to have no connections to other elements whatsoever. Okay, and that is why this is called the discrete topology. Okay, so that is the intuitive view then of why we go to this set of subsets of the set capital X to capture this notion of what is next to what. Okay, right. So now what I'm going to come back to is the final, in this final bit, is the initial plane problem that we had. Okay, so I'm not going to do this rigorously at this stage, but I just want to explain how the concept of defining a topology on the plane then captures the notion of what is next to what. Okay, so let's redraw out the picture of the plane here. Okay, so here is my plane, and we'll have our set capital X, which will contain loads of symbols which will be representing the points in my plane. So here is my point P here, and I'll just colour in my plane in orange, like so. Okay, right. So a topology then on the plane, on this set rather, we're going to define a topology on this, and this is going to be a set of subsets of this. Now I'm going to show you a topology, the normal topology that people would define on the plane. Okay, but I'm going to do it in a non-rigorous way at this stage. Okay, so the non-rigorous way that I'm going to say how we're going to define the topology is we're going to define the topology, we're going to define the open sets of points from this plane as the sets which do not contain their boundaries. Okay, so sets that we will draw like so. Okay, we'll draw them with dashed boundaries like so, okay, because they contain all the points inside this line, okay, like so. So they're going to contain all the points that I'm highlighting in orange here, but they're not actually going to contain the boundary here, okay. Now, they don't necessarily have to be all in one clump like this. They could be like this, okay, so you could have this lump and then another lump over here, just as long as the two lumps together don't contain their boundaries. Okay, right, so I'm going to put in my topology then all subsets of the plane of this form where they don't contain their boundaries, like so. Okay, and that's the normal topology then to have on a plane. Okay, now, to try and explain why that captures this notion of what is next to what then, okay, what you're going to do is very much analogous to this, although it becomes slightly less rigorous now. Okay, so what we wanted to do to capture the notion of what was next to what in this plane was we wanted to have little lines connecting this point P to the points that were infinitesimally close to it. So to go back over, remember, I wanted it to be the case that when I zoomed down to an infinitesimal scale, and I know this isn't rigorous, but this is the intuitive picture that I want to give you. When I zoomed down to the infinitesimal scale, I wanted it to look like this, with this array of points connected to each other by little lines, where a point is connected to the points that are infinitesimally close to it in this way. Okay, so this captures this because any one of these sets that doesn't contain its boundary like this, that contains P, okay, so I'll draw one that actually does contain P, and I've drawn it rather badly there because P actually looks to be on the boundary of that orange one. So I'll draw a fresh one here. So if we've got a set of this form that I've just described, which is in my topology, one of these sets that doesn't contain its boundary, okay, such as this set red here, and it contains P, can you also see that any set of this form that contains P will always contain the points that are infinitesimally close to it? Okay, because firstly, you're not going to have, one of the elements that is certainly not going to be an element of the topology is a set that just contains a single point. That is not going to be one of these open sets. Okay, it's not one of these sets that doesn't contain its boundary, okay, because the point is its boundary. So that is not going to be in this set of open sets, okay. But when you do have a set that does contain P, I hope you can appreciate that if it doesn't contain its boundary, it will also contain the points that are infinitesimally close to P, and therefore going back to our way of working out what points in the set are going to have lines drawn between them, okay, the points that are infinitesimally close to P will end up getting lines drawn between them and P, because they will be with P in all of these sets in the topology that P appears in, okay? So that intuitively then is how we can capture this notion of which points are connected or which points are next to other points in this set by defining this topology, which is this set of subsets of the set capital X. Okay, and I think I will call it quits there whilst I'm ahead, and we will move on with our discussion of topology in the next video in this playlist.